Yes, now let us get started. As we have two topics we are going to cover today's session, and I'll be talking about power integrity inside Altium Design, which is powered by Keysight. And our guest speaker, Mr. Mahendra, Sales Solution Engineer from Keysight Technologies, is going to talk about the EP scan for the basic security analysis. Now, I'll be starting with power integrity uh, by using power analyzer powered by Keysight, and followed by Mr. Mahinda is going to demonstrate the EP scan capabilities. Now, let us uh, have a look at the agenda of the power integrity made single topic, followed by we will be passing on to Mike Mahinda for the security topic. Yes, this is my agenda for the power integrity. We're going to talk about the what is PCB power integrity and related risks, and designs more susceptible to power integrity issues, and downsides of traditional power analysis methods, and optimizing power analysis in Altium Designer, and Altium power analysis demonstration, followed by summary, and Q&A will take at the end of the both the sessions. And you are always welcome to enter your PDF questions in the chat. We will answer your questions at the end of the session. And this session is a recording. We will share the recording to all the registered and the participants. Yes, power integrity refers to the ability of the power supply network to reliable, provide the clean and stable power to all components while avoiding excess voltage drops, current density across the boards that can damage the PCB and lead to reliability issues. There are very famous Eric Bogatin. We have the quote from his book. The primary difference between the PDN and signal paths is that there is just one net for each voltage rail in the PDN. It can be a very large net that can physically span the entire board and have many components attached. As we all see, the PDN is like an ecosystem. If one small part of the PDN were to change, the entire system performance can be affected. This makes generation very difficult. Now, what are the risks associated? Well, the poor power integrity on the PCB creates many risks in the design because of the tighter noise margin and lower voltages for the supply applies the power integrity becomes very important. With these margins are exceeded, all scans can happen. If the designers design the PCB by keeping the power integrity in mind, they can reduce the overall power consumption of the design. If the designers designs the PCB without considering the power integrity, in mid the failure components can occur. It could be the transistor enter into the ambient state that can put extra stress on the component, and the same dynamics stress can result in fluctuations in the power rates, and the interference with the signal path can degrade the signal quality. This can lead to signal integrity and power integrity issues as well as EMI and EMC problems. If there is excess current flowing through via the region of plane, the board can be damaged and delamination will be happening. As we just reviewed, a poor power integrity can impact the end product in terms of reliability and performance. However, the result in increased cost and other impact is delayed product releases. This causes by fixing the design problems increase by factor of 10 as you progress. To the design cycle, the cost of finding the design flaw at layout level is cheaper than the catching the problems in prototype stage or post-production stage because the power integrity has not been top of the uh, mind issues for layout designers like, for example, DRC. These issues are generally uncovered until you go later in the design cycle. This leads to time-consuming activities, design changes. Maybe you do have to go for additional prototypes, testing time, and retooling. Market window can be missed in terms the product delivered to the customer will be missed. So what is the alternate way? The alternate way is to wait and see. The productivity philosophy is to make the power analysis a part of the PC design process. Power integrity early and often throughout the layout process maybe it will provide better identification and elimination that you can meet the costing of the product. The implementation of such power utility philosophy can be viewed as, you can say, you can take a business policy, the PM cost to implement orders of magnitude and less than cost next outlined. How design more susceptible to power utility issues. That generally nowadays we are dealing with handheld, wearable, and IoT devices typically require high dense layout. These designs are more susceptible to power integrity issues, and the reason is limited space available for the power supply. However, careful placement and routing of power supply are required to avoid the voltage drop and noise in power supply. And the next comes analog mixed signals designs, including the data acquisition systems, are mixed signals, caps, and discrete analog devices, and others, and the class of designs susceptible to power issues. The analog components require stable power supply voltage just to assure the proper operation while minimizing the noise and distortion. The digital components in the mixed signal also require stable power supply designs to avoid noise, margin, and potential significant issues. The high performance platforms will include the microprocessor, signal processor, FPGAs operating at maximum clock speeds are particularly susceptible to power utility issues. Designs with high current requirements such as power amplifiers, motor controllers, and LED drivers, these can consider design are susceptible to power utility issues where they require stable power supply and low impedance and get ample of current for the components. Downsides of traditional power analysis methods. The traditional power integrity analysis tools are expensive and even more than actual design tools. And the process to use the analysis tool is typically destroying the due to the designs once burn the valuable design time and losses valuable time in the momentum going back to and forth PCB level tool for the analysis tool. And do the simulation, and if there is any changes or to clean up required, and it like jump back and forth, which cause problem, delay, and lot of focus, loss of focus. These power integrity tools are typically complicated, and no point is these standalone solutions are not integrated with the PCB design tools. You have to change the smallest change to design to make the design change, and you have to go back to the PCB tool and get the results. And everything, as I mentioned earlier, it is a completely wasting your time and something you can't get back. Optimize solution inside Altium Designer, where Altium offers the solution which is integrated inside the tool itself. The power integrity analysis is efficient and simple in Altium Designer. Your board design, you need to open and choose the option Power Analyzer by Keysight from the tools menu. No need to leave the Altium Designer and no need to export the design. All data is self-contained in the Altium Designer. Once you define the board power network as shown here, we just simply click on the Analyze button, and after simulation, execute results and displayed as shown in the highlighted. It's just another tab inside the Altium Designer, and you can go power back to the schematics and PCB, and you can do the changes over there based on this failure, and you can again quickly pop back to this window of PDN network, and you can again analyze the analysis. We can use the current density heat map on your Altium board designed together with the legend of current density values. You can see here. Let's say if you are looking for voltage drop similarly with the legend values, you will see this during the demonstration in detail. You also have an option where you can easily probe the locations. Let's say looking for some images you want to capture in the report along with the general reports of power analyzer. In this, you can go and probe the location where are you interested, and even capture images that can be included in the report. This is another benefit you will get with the Keysight power analyzer. This we will see during the demo in detail. Sorry. And we have a section to see the report. Click on the view field report and see the desired power supply network, and also you will see the entire PDN network report. And you also get some expert's opinion needs to change to overcome the issues that you can implement in your design. You can also see the report in HTML format and easily share with the collaborators. Here I have screenshots how you can capture the own images during the report generation process, and that can be highlighted or can be taken to the part of the report and shared with the collaborators. Now let us have a look about how we can perform the power unit analysis inside the Altium Designer and the PCB without moving to any other tools. Now let us have a demo the software. See here, I have opened the Altium Designer. Now you can see the PCB in 3D view. Now it's in two-dimensional view. And if you take a close look at our circuit, we have the power supply section where you take a close look at the schematics. It's opening. We close up this browser. Yeah, this is the main input source to our motherboard PCB from J4. We are getting the input voltage, and from here we are getting the 12 volts. And this 12 volts is being converted to 900 millivolts, where you'll be seeing here the 12 volts here the input. This is a regulator, and we'll be getting here output as 0.9 volts or 900 millivolts. And further, this 12 volts will be converted to 3.3, and further this 12 volts will be converted to 5 volts. Now we are going to perform this power unit analysis on a portion of this network to see how we are getting the any kind of issues in terms of condensity or voltage drop. We'll be able to find out with the help of the power analyzer powered by the Keysight. Before we jump into the analysis session, first we need to make sure that we have installed the extension or not, because it requires separate license. And the extensions I have already installed for analyzer powered by Keysight. And usually it will be, if you not installed, if you go to the purchased tab here, you'll be able to find the power analyzer here. Once you install, it will be shown under installed. I installed this, and you will be needing a separate license apart from the Altium Designer. You can see I have the Altium Designer and I have the a separate license for the power analyzer, which is powered by the Keysight. This is very important. Without this valid license of Keysight license, power analyzer and Altium Designer, we can't perform the analysis inside the tool. And once we have the extension installed, and once you have the valid license, you can able to quickly launch the command of power analyzer powered by Keysight by going to tools or analyzer by Keysight. When you click on this command, you'll get a kind of new tab will be opened, and it's going to load in the all the DC nets. And I'm just highlighting this power analyzer by Keysight is available to perform the analysis on DC nets. And now I'm not going to configure the network, which will take a huge time in configure the network. I'm going to load a pre-configured network which I have prepared for this webinar. These are my pre-configured PDNA network, which I'm going to use this to perform our distribution analysis on the design. This is my network. And before we are going to discuss about all this network, we need to set up some global configurations where we need to access from here. And the first and foremost thing is, we need to specify what is your maximum current density per surface and inner layers, and minimum and maximum via current, which is very important. And if you want to skip the ground plane, you can able to uncheck this to skip the ground plane, but which I'm going to take to use ground plane to do the analysis. I just enabled. And you can also select the copper type you're looking for. You can also have custom. You can able to enter the custom values, and you can able to enter the ambient temperature. And another thing is what nets we are going to define. We have enabled, and based on the names, tool going to select the power nets, and what other components designators we should detect. We are given the requirements. Here I'm not going to change any settings. I'm going to leave it as this default. And coming to the configuration, as I told, we have this J4 is the main source of the voltage store network, and we are going to run the analysis on 0.9 volts. I mean 900 millivolts, 3.3 volts on the 5 volt section. Hence, we have the J4, if you get to the settings, you can see the type of it has been recognized. It's 12 volts, and output is power input, and therefore having ground. And we have got the load, is a source, and we have got the loads, V10 and so U10 and U23. These are the regulators, voltage regulators. And if you select here, by default for voltage regulators, we can able to choose what is type of regulators they are, linear SMPS. Recipe sense, we can select these are the VRM linear, and we have to select the what is input. And this section input is 8 and 12 volts, which is input, and output is 8 and 0.9 volts section, and again region is the ground. Okay, just click OK. And coming to this one, similarly we have to choose the input is main 12 volts, and output is 3.3 volts, and again it has the same ground pin U23, and 3.12 is output. I'm not going to change these settings. I want to keep it as default. Okay, and we have got the other networks configured. You can see here, and if you take this one U1 regulator, this is the IC current, this is the load. As you can see, we have got the source and sink regulators, and automatically those regulators network has been created will be formed, and have added the what is the sink for this load, sink for these sources. And for this U10, U1 is a load, I mean sink, and you can see the what is the pin current. It will be shown here. Sorry, pin current will be shown here, and if you want, you can able to change that current value as well. You can see the type with the IC current. Okay, now I'm going to show you how we can create a network by using this power analyzer tool. Now we need to create a network of 5 volts. You can see there is no network for 5 volts. We have only network for 3.3 volts and 0.9 volts. I mean 100 millivolts. Now let us create a network for 5 volts, and then let us perform the analysis. First, to create a network, we have to extend the nets, and we need to add the inlet main 12 volts fused. If you take a look at this here, the 5 volts, you can see these are 12 volts input, and we have got a fuse, and from the fuse connected to this regulator, and the output is coming as a 5 volts. We're going to take this as a fuse network, main 12 volts, and this is the network that to choose, main 12 volts fused for the analysis. Okay, that's why we have to choose the main 12 volts fuse. Okay, extend net, main 12 volts fused, and automatically the two components will get added, fuse and then transistor. And now click save, and then here we need to add the regulator. The regulator is U12. Just manage and U12. You need to enter. Okay, U12. Okay. So once it's been selected, we need to select the VRM linear, and what is our V output? The 5 volts, which is very important. And here we have to select the mains 12 volts fuse, and here it is IO 5 volts. We have seen in the circuit. This is the input and this output, and the ground is VM 12, and click save. Once you add that load here to the J4 main source, you could see automatically a 5 volts network has been created. Now we need to add the sink, I mean close to this U12 network. For this, the U12 network, we have U22, 25, and U19 are the loads, I mean sinks. Just save. And this all this having IC current of 150 milliampere, I'll be keeping as it is, and I'm going to disturb. Like this, we can quickly and easily create the whole networks, and you can have to perform the analysis. And if you take a close look at the right hand side, you can see we have can specify the DC drop limit. What is the DC drop limit? You can specify, and if you want, you can have to change it to based on the requirement, and you can able to perform the analysis. If you click on the showing the tree, then the network configuration, you can able to see here. J4 12 volts to 5 volts, 12 volts to 3.3, and 5 volts will be connected to these sections, 3.3 to these sections, and 12 volts to 9.9 and 0.9 to this section. This is the network we have to see clearly. Now I'm going to run analysis for this particular network. Just click on analyze. You can able to analyze for all nets as well, and also you can able to analyze only for one net. Okay, just click on analyze. Now you just perform the analysis. The main reason to use this one is it aims at ensuring that adequate copper has been provided in the path and voltage sources to loads, and also, in other words, the planes, tracks, and vias on the board having sufficient size of copper to meet the power consumption requirements of the device on the board, and also it analyzes DC performance based on the electrical and physical properties. And you can also specify the nets to be analyzed, and the added advantage of this power analyzer powered by Keysight is this is a part of the Altium designer, as I have highlighted within my presentation. And you need to take your existing PCB and you can just run the power analyzer command from the tools menu, and it is going to show the analysis configuration. Once you configure, you have to quickly get the reports. Yes, now the analysis has been completed, and you can see it has got a file report. We have got three categories. Voltage drop is 133.9 millivolts, and you can see there's a condensed issues and the maximum current via issues has been found on the PCB. Now let us go to the PCB and let us take a close look about the analysis results powered by this power analyzer. Let's click on show on PCB. It will be able to show the results directly on the PCB. This is the thing. You can also look at the power section, the ground plane. And if you go to the panels, we have a dedicated panel powered by Keysight. And you can see we have got a lot of violations in terms of via current and current density. If you want to clear this, you can just click on all to clear. If you select on current density, there are violations associated with the current density will be shown. And I think we don't have voltage drop issues. And it seems we have the wire current issues. If you select the error message, it is showing this having a issue of wire current, which is out of limit. Maybe we have specified particular wire current only handle 1 ampere current, and here it found it is 1.2. That's the reason a tool has flagged an error, because we have seen in the beginning the universal configurations where we can be able to specify the minimum wire current and maximum wire current. Based on this, tool will analyze it and it will flag an error if the particular via dia is not sufficient to carry that amount of current to flag an error. And current density, it is flagging, and you can see here the connector path here, which is smaller in between these vias, which leads to the more current density at this area. Like this, you can able to quickly find the errors, and you can just quickly go back to the VI editor, and you can able to edit the values as per guidelines. And again, you can come back to the power analyzer, and again, you can quickly run the analysis where it is all the part of the Altium Designer unified solution. And you can also see the heat maps. You can see the current density heat map, and you can also display the current direction, the direction of the current flow inside the this particular plane. It will be shown in the arrow directions. You can see the direction of the current which is flowing, and also you can also see the voltage drop here inside the this power analyzer panel. This is the voltage drop. You can see we have got the more voltage drop is being specified here, and you can able to see the voltage drops in terms of, you can see we have got the legend, which will be having the marking of the voltage and voltage values. And you can also look at this one in the percentages. By selecting the percentage, it will be changing the values in terms of percentage. And you can also enable the visual slider. You can able to see where the 30% of current and which are voltage, and where you have the 50% of voltage, where you have the 70%, where you have 70 to 100%. You can see the visual voltage contour. You can see this up to here we have a 30% of voltage, up to here 50%, up to here 70% and less charge is a 100%. We have the more voltage drop has happening in this particular section. And likewise, you can also go to the current density, and here also you can have to having the linear and logarithmic scale, where you can have to see the difference between the two scales. Is the logarithmic scale, and we have the linear scale, and we can also adjust the scope of controller by using this slider. Suppose you want to have the results for a maximum of 100 ampere mm scale, you can have to change the slider, and it will optimize the results based on the slider. You can have to see where you have got the more amount of current density deposited on the PCB and we show. And also we have option to class flow, and this can be added to reports. Just can have to select the class flow phase, which will automatically highlight the what is the maximum current density will be shown here. And once they highlighted, you can see the what is the current density value, and you can also add this to report and see it to make actually, and we want to have this one to be added to a report. You can add, and the same way you can go to heat map, and you can just set the voltage drop. You want to have the voltage drop to be captured in a report. You can also select add to report. These images, the screenshots will be generated as a part of the report. Okay. Now, like this, you can be able to perform the current density and voltage drop and wire current analysis inside the Altium with the help of the analyzer by Keysight. Now, we'll go back to this our network, and once we have done the results, we can able to go back to the PCB and I can able to do the changes and I can able to perform the analysis. Once everything is completed, we are now good to generate the reports, where you can able to use this option view report, which will help you to generate the report for this particular network, and you can also generate a network for the whole network setup as well. Now it is being generated in the process. Now it is generated in the process. Yes, it's very easy to use too, and there is no much inputs required. We just need to select the networks, and we just need to enter the what is the input and output voltage and current values, and then we need to specify the what is the maximum wire current and minimum wire current and current density and inner layer current density values. And once it's been configured, yes, we need to click on analyze. That will automatically use the existing PCB which is being done inside Altium, and then it will analyze it and it will give a report, and that report can be easily generated with a help of this power analyzer, which will be given in HTML format, and you can able to share that report with your colleagues for further analysis. It's very easy to use too, and for the DC analysis. Okay, and I think let us wait for a few seconds. It is taking a bit time in generating the reports. I hope I think this will be very helpful where we want to perform the power analysis on the DC nets, which is integrated inside Altium. Yes, we have got the report. You can see what is the metal conductivity and other parameters, layer stack information, and the parameters weight is paid, and some expert opinions to improvise this result. And to go a little bit down, we got the screenshot of the networks where we have this is the round plane is referring to 0.9 volts. Each layer will be having a separate report, and it's a complete detailed report which will be given by Altium. You can see here we have got the current density, and it's a complete detailed report. You know, to look after the any kind of images. You can see the voltage drop here, the voltage drop, and the network what is being configured and what is the which network you have performed the analysis, and what is the current and what is the status, and these are the current values and current density and the diameter information of each net. Okay, and I can able to give it as a report. You can able to select all these data and just click on the generate it. Once you generate it, you'll be getting the report in terms of HTML. You can just open the network like this, and you can able to see the complete results of your network heat map, voltage drop. This like you can able to perform the analysis inside the Altium by using power analyzer like this. I think that's all from my side about the power analyzer. And Q&A we'll take at the end of the session. I request you to type the questions in the chat. I think Mr. Mahendra, over to you.
Yeah, thanks, Sairam. Let me share the screen. Right. All right. So just confirm you're able to see the screen.
Yeah, Mahendra.
Right. Thanks all. Right. Okay. Hi all. So my name is Mahendra. So I'm working as a solutions engineer at Keysight. So mainly handling HSD solutions for pre-silicon analysis, like signal integrity, power integrity, and memory design solutions for all the EDA solutions. Like you can use these tools for any kind of CAD analysis. So today the topic will be on the EP scan. The analysis will be mainly with respect to the CAD level, where we give you a first order applications where engineer can himself do analysis instead of waiting till the SI engineer taking the job role for the analysis part here. Let's understand why the challenges here, why these tools is required. So most of the time, so on the layout engineer side, so we just input the constraints through other schematic. We just place route and finish the task till the Gerber generations or prior to Gerber. So we just send data to either a hardware engineer or pass on to this data to SI engineers to do all the SI analysis. So it's something like we are dependent on the SI engineer for almost all every net on the board file. Okay, every net on your board file. So you need to wait his response then to do all the modifications on the board, modifications like track fit changes, if it is any which issues with the impedance, or if it has any issues with insertion loss data, right? You change the Manhattan length on your layout tab. That's a challenge is what we see. So your dependency on the SI will be more. So just before we start, so just want to have an understanding on the impedance requirement. So can you just, Sairam, can you just pose the poll question first? I just want to understand the team here, how many of you are working on an impedance matched board file? Let me see the response. So we'll be talking more of an electrical level here. So we take the CAD and do some kind of electrical checks on the board file. So just post the poll question.
It is live now.
Okay. I don't see the poll. Right. So Sairam, you can just explain, like you can just let me know what the poll response.
Yes, yes, yes.
So basically, I want to know how many of you are managing the impedance on your board, how you're managing the data, either in terms of any capacity calculators we have or a constraint like a thumb rules we get since it's a repetitive board, right? So there are instance customers they work on a board which is a revision board file. Okay.
I think Mahindra, we have got few responses, and most of the people given an answer that they are taken care by SAT,
As a team.
and few people answered thumb rule or IPC calculations.
Okay, great, right. Okay, so that's a idea here. Okay, let me take my pointer again now. So here we have a mixed approach. So that's expected data, where we have customers where they depend on the SI rule or they do an thumb rule or IPC calculators. But you don't see any application where once you use any IPC calculators, right? So you can't analyze those nets. Okay, so what we again we wait for the response from my SI engineer. Okay, so you've used the IPC calculator data and finished all your layout drafting in terms of placement and routing. Then how to identify the issues here? So what we have done is we have developed something like an app-based concept where a layout engineer or a hardware engineer, okay, so they can identify these issue at CAD level itself. So that means it's a quick simulation. Okay, you can always argue, okay, saying that, okay, this is not my job. This is an SI engineer job. I am not an SI qualified to do all this kind of analysis. So you don't need any high-end SI knowledge here in this case. We are doing a quick simulation, identify the quick analysis in terms of impedance mismatch. Okay, so as many of you are aware, right, when you see an impedance mismatch, so best thing what we do is we change the track widths using any IPC calculators. But we should be knowing once we finish the board file on my layout which of the nets the impedance are not patched, or what are segments which are not matched, or what is the discontinuity happening on my layout file. So you need some kind of quick analysis on the layout after routing. Though you follow the IPs calculator, there are instances you might tweak the parameters to adjust the real estate on your layout file. So idea here is to analyze on the fly between the layout engineers and the hardware engineers, and you can quickly identify these errors and modify this data with respect to the layout constraints and update, and again you can run the analysis part. So we are not trying to replace the SI role here, so let me be clear on that part. Okay, so we will be doing quick simulation, so it's something like we are reducing most of the tasks which need to be undergone from the SI engineer. So once we finish the quick simulation, so we will be sharing this data to SI engineer, where he'll be analyzing for different standards. So on this part, let me talk about quick standards part. So Sairam, can you just pose a poll too? Just want to know how many of working on a different standard, something like DDR based board. Are you following in DDR compliance or a PCI or a USB or any single-ended constraints, single-ended node nets has to be passed with this impedance, right? There are some standards. Are you following these things? Sairam, can you just pose the poll too?
Yes, it is in progress.
Okay. And let me
We are
know once
getting
it's
responses.
complete, and let's see
Yeah,
how the response.
yeah.
So do you follow such some guidelines like this, or just want to know on that part? So this is the data which you get based on the standard, like PCA Gen 4 has one set of impedance match, or your intentional loss, return loss should be this much, or Gen 5 or USB 3, or latest is USB 4. Similarly, if you're working on any differential, basic differential impedance matched track, right? You must have this much of impedance on this net. So are you following any such kind of guidelines on the layout?
I think we have got most of people said yes.
Okay, that's great.
And
So then probably I think you will be able to correlate the things what I'm going to cover the next. So what we're trying to use is an import data of the CAD. So we import either through OTP++ or through IPC251. So all on the fly, you can take the Altium data also through OTP format or IPC251 format. Run this app, okay, and you can quickly do a simulation and get the results and the reports. The HTML report, what Sairam was showing, right? On the similar line, you get this report. So this works like an app for you where you can use this layout, the ODB data, run this EP scan, and get the results like this. Okay, what is my impedance profile of my of the net selected on my board file? So generally the critical nets like DDR nets or address nets or any clock nets, right? We analyze, or any PCI nets, we analyze those nets for any impedance match or any kind of insertion loss or return loss. What is my data across my uh, critical nets on the board file? So you get this quick results. So this tool is not any multi GUI. So this is single GUI. You get only one graphical window where just import the board file. You get the entire list of nets as it is what you use in your CAD file. The stackup also gets imported when you import the CAD. You don't need to specifically create a new substrate. You are free to update substrate with updated changes, like any electrical performance you need to modify in terms of epsilon value or loss tangent, right? That can be changed on the fly. So you can just select few critical nets, add to your test plan. Okay, you can run this test plan and quickly get those results like this. Okay, so this is the standard I was mentioning. So if you follow the standards, right, it will give a plot saying that, okay, this is my insertion loss. So this we can apply saying this PCI different take standard. Is it passed or failed? So user can create his own specifications as well here. So it is not limited to what we are providing. You can define your own specification. What is your insertion loss data, the magnitude data? What is your insertion loss, return loss data? And you can run those specifications on your say lines on the fly. Similarly, you can also get the insertion loss data here, where you can see uh, all your this nets are passed for this PCI 3 example. Similarly, you can also plot the TDR plots also. So TDR plot, I'm sure most of you have heard about TDR. It's called time domain response. So this will give an impedance profile, impedance plot against your time, where you can see there are instances you might see sudden spike in your impedance of the net. So there are various reasons. You might have increased the track width or reduce the track width at certain area to provide proper electrical connectivity, electrical uh, heating joule effects there. Or there are instances you might have a used wires as well, so you can see all this kind of impedance spikes also on any critical nets. So you can plot this TDR and see whether as per my PCI specifications, this TDR plot are passed or not. Okay, this is about the EP scan overview. So the idea here, it's a quick simulation which we run on my layout file. Okay, so we just import the ODB or IP251 and you can run the simulation and get the results in terms of plots as well as the HTML report. Let me take you to the demo. Okay, so this is an EP scan tool. Okay, so let's take any of your EP scan project. So you import the, as mentioned, you can import the ODB or IP251 data. This is a GUI of EP scan. Okay, so design is already loaded here. So if you want, you can see the stackup. This is your stackup, which automatically gets imported whenever you import your ODB or IP251. So now, if you want, you can change this electrical parameters. There are instances. While you're doing layout designing, right, you might not worry about this conductivity or loss tangent data, because your intention will be more when you do a layout is in terms of thickness. These are physical parameters which will be considered. But when we go for any electrical checks, you need to have these data also in terms of conductivity, dielectric constant, loss tangent. Also, we support H angle of the stack up of each layer on the board file. So if you want, you can update this in case if this data is not available in your layout substrate. So once you have this, you get all the list of nets what you have seen on your board file. Okay, so you can just select any of this bunch of nets. Say, let me take a quick 8-byte DDR in this case. Okay, so I'll just select all this DDR at one stretch here. Okay, so we have this test plan. This is one of my test plan. I'll just hit the run test plan here in this case. The simulation is quick. You don't need to do any kind of port assignment here in this case. So all you are doing is with the list of nets what I got from my CAD import, right? I just chose the critical nets. Generally, critical nets are used like DDR nets or any clock nets or DP nets or your PCI nets. So those bunch of nets, I just pull onto my test plan and hit a run test plan. So now the simulation is happening at the backend. It creates the parameter data at the backend. User need not worry how to create this parameter data and again load this parameter and get the plot for insertion loss or return loss. So it automatically calculates the S parameters and does the simulation at the backend. The simulation time, depending on your hardware, right? So it hardly takes about 1 or 2 minutes, max kind of 3 minutes time in this case. It's a quick simulation tool. What you see, it's a electrical level checks in this case. Uh, there are some default specifications which we provide along with the tool, something like you saw on my slide, right? Like PCI specifications, as well as for BDR specifications. User is free to create his own specification as per the boards he is working, and you can use it as a template also in this case. Now you can see here, this is my impedance. This is a DDR net, and this is my data as per the impedance data. So for if I select DDR4, right, I get to see what is this on this DDR4 net A0. What is my delay? This is the output results here. So this is the impedance profile of this DDR net. What is my skew? So for especially for memory designs, right, we try to get the skew measurement. So as I asked in the poll question, right, there will be standards where you need to maintain at least minimum limits with respect to this skew also. So you get to see the skew and what is the impedance, what you're getting on this net. When you click on A0 net, you get to see the segment wise details as well as the via data also. What is the delay? What is the impedance across each line? So this is running at a different layer. And again, this is running at a different layer in this case. And the via what is being used here. So all this data will be plotted. So this gives an idea here for you whether my net is optimizedly targeted for any impedance here. I can run this on a specific specifications. I can just choose, like, I'm running for any DDR4 impedance. I can just hit a DDR4 impedance. I can just plot, see now whether did I follow all the DDR4 limit or not. So I can just choose DDR4 or DDR5 kind of thing. So you have this default specifications as mentioned here, or I can choose a quick single date based impedance checks also. The specifications mentioned, so you can choose as based on standard. Then next we have this insertion loss data. So along with the impedance checks for the same nets, let me select all the nets here. Yeah, so you can at one stretch you can plot the insertion loss data. So you can see the insertion loss here. So I think somewhere going, let me put a cursor somewhere across this point, right? So this is insertion lock, it's about -3. So peak in this case -3 till it's going almost to say about -60 kind of thing. So you can again check this against for any specifications as well here, like any DDR, PCI. And at the first instance in the impedance, if you don't uh, achieve the impedance target, right, as a layout engineer, I have got a flexibility where I can go back to my board and tweak the line parameters. If I don't match with the impedance, I can change my width and again reroute and update back to the analysis here. Similarly, in the insertion loss data, I can change the Manhattan length and see what is my insertion loss effect, as well as the terminations can be modified here and see what is my insertion loss, whether it's within my permissible limit or not. Similarly, you can also plot that return loss data. So you can see the return loss data, all these aspects as a layout engine, right? So you don't need to break your head, getting this setup like in a port assignment, then calculate the parameters and then plot your IL RL data, right? So this tool helps you to on the fly plot all the insertion loss, TDR, return loss data, and also the TDR plot here. So this, you see the y-axis in this case, it's an impedance. Again, the next axis is your time data here. It gives an impedance profile over the spectrum of time data. In the recent update version, we added an option also where you can just give something like an quick suggestion or an overlook where it tells you that, okay, what is the description, what has happened at this junction, right? It tells you at this frequency, across at this resonant frequency, there was stub kind of thing. And similarly, we also have option where we can see the written part discontinuity. So this is very much critical. So if you don't provide a proper return path, right? So as Sairam was mentioning, so the end issue will be your EMI or any kind of termination losses will be coming into play, where you get to see more coupling issues or any peak IL or RL data. So this is a quick description of what it gives, along with the along with the exact location and the net as well as layer for you. So this way, on the fly, you get to see the results, and user also, as mentioned, you can manage your own specifications. So these are specifications what we have built in available. For example, DDI specifications or PCI or any single ended. So if you're not working with all this kind of PCI DDR, right? So I'm sure most of you are working as asked in the poll one question, right? So there will be some impedance matched nets on your board file. So it's not like these tools are made only for PCI or USB or DDR board based designs. So even though if you have any DDR or if you have any differential pair or any single-ended nets, right, you can apply this EP scan simulation on the layout file and get the results quickly here. So if you observe here, so we didn't use any kind of multi GUI tool. So just import the project, view the substrate, what the project has got, or if you can modify, and select the nets which you want to for simulation and plot all the impedance response, IL response, and RLTDR plot response here. So this is how you can quickly do a simulations. Once the simulation is done, you can create a report, click on generate report. So this will create an HTML report kind of thing, which can be given to your client or manager saying this, okay, these are nets I analyzed. Okay, this is a stack up what I used. Okay, so I analyzed this board for impedance. What is my impedance? What is my skew data on this net? Okay, and section by section also it will show this data, like across each line, what is my start and what is my end data, what is my return path. If there is a return path available or not, it shows your return path as well, and it's insertion loss. So this HTML you can just share to your manager or your client. So and you can see if this is what they're expecting, right? You can go back and generate your Gerber on the fly for the board file. So now you can see the dependency to get these reports on the SI is drastically reduced in this case. This is all about the EP scan. So this is a tool which works for your second at the first order second to get all the insertion loss, return loss, and the TDR plot of your PCB board files. So that completes my demonstrations. Any questions from your end or any